So it's a real pleasure today to introduce Alla Sheffer. And so Alla's been on faculty here since 2003, I believe. And so this is after she did a postdoc at University of Illinois, Urbana-Champaign, and then was on faculty at Technion in Israel. So she works in the area of geometry processing, and so as you all know, it's easier and easier to collect enormous quantities of geometric data, either coming from a connect or a stereo algorithm or from models you find on the internet. And so coming up with general methods to process this data and deal with it in a meaningful and easy fashion is really a key problem today. So she's very well known for her work on surface parameterization. So a lot of her algorithms for that are found in a variety of commercial CAD packages around the world. And she's also done a lot of work on developable surfaces. And so these are surfaces which you can flatten out without any distortion. And so in the last 10 years, computer graphics folks have found out that it's really important to clothe your characters well. Surprise, surprise. And so so there's actually a really rich body of work remaining to be done there. So her work has been recognized by a number of awards. So in 2009, her PhD student Abiryu Popa won the 2009 Alla Sheffer PhD dissertation award for best graphics dissertation in PhD dissertation in Canada. Our master student, Ron Maharick, won a Faculty of Science graduate prize in 2012. She won an NSERC Discovery Accelerator Award in 2012, and in 2011 she won the an Audi Production Award, which is for a really neat application of a collaborative. It was a collaboration with the University of California for toolpath generation, which has some really interesting connections with projects that she's been doing. Yeah, and so last thing I'll say is that often when you drop by her office, she can often be found Skyping to some other. She collaborates all over the world. She can often be found Skyping to various corners of the world at any point in time. And her other hobby that I'll embarrass her with is trying to persuade laid-back Vancouver drivers to pick up the speed a little bit. Having said all that, her talk today is Quantifying Design, the geometric properties behind designer choices and human perception. So welcome, Alla.
Okay, so how does all that relate to computer graphics and computers in general? Well, let's start with a picture. So you raise your hand if you sort of can see what kind of shape is drawn here. The 3D shape. Can you recognize the shape? Hey, not everybody. Yes, everybody. How many of you understand what's the functionality of the shape? What is it? 1%. Good point. So we can recognize the shape even though we don't recognize functionality. And that's important. Why? Because functionality is something computer vision has been looking for a very long time. Like, how do you recognize a cat? And if you have a database of cats, you can figure that out. What I'm interested in is how do you recognize shape without knowing what its function is. Here's another example. Again, how many of you think you have a pretty good sense of what this shape is? Just raise your hands. Good. What about this one? Any opinions? None. Good. So what's the difference? Those two were just drawn by designers. That was a scribble. Well, actually it wasn't a scribble. It actually is a 3D surface and from some project I did a while ago. But those two are drawn by designers. And well, when designers draw something, they actually want the audience to understand what they had to do. It's sort of part of the expectation that if you draw a design of a shape, you want people to understand it. And what that means is you don't draw just, let's say, the type of lines that people who come from computer vision, for instance, are used for, which is things like silhouettes or feature lines. Because if you take this object in the middle. You draw its silhouette. I think by now you don't understand the shape, right? It's a very different shape. You have no clue what exactly happens there in the middle. So the choices that artists make really are there to help you understand what goes on. And artists are aware of it. Here is another example. Those are actual artistic drawings, or artistic design sketches. And, well, you sort of might have an overall idea of the silhouette of the object. But what do you think? What is this? Is this a beanie shape? Is it a chair? Maybe, maybe. The same here, right? I mean, sort of something boxy-ish. But if I were to ask you to describe the surface of what goes on here, it would be very ambiguous. And when artists draw shape, they want that shape to be understandable. So in fact, the way those pictures were created was by deleting a bunch of lines which actually artists drew. Notice that those are not lines which actually show up as features or as silhouettes in the actual shapes, right? None of those are actually delineators of regions or sharp features. Those are lines which you will not actually have on those shapes if you look at the real object. Those are lines created by artists so that we, the audience, will actually understand what we're looking at. And those are the lines I'm going to talk about for the first half, maybe a bit more of my talk. Those lines are known as cross-sections. And what we are interested in is to try and use them to be able to understand what actually goes on in the drawing. So what we want to do, here's our goal, or what we do is, we start from this type of drawing. The orange lines are the same set of orange lines you have seen before. This is what's known as cross-section lines, that's what design literature refers to. And the only consensus in design literature as to what a cross-section is, well, it's an intersection of your surface with a plane. And if you look at each one of them, you can visually understand what planes those are in 3D, right? And somehow, with the help of those lines, we understand what this shape is. And that's what we are trying to get our algorithm to do. Why? Well, because if we have an understanding of shape, and here what we're aiming is to understand the directions the surface is pointing at. In other words, what we are getting out is a normal field. So where does the surface point to? Here color encodes direction. So blue is sort of pointing along this axis, pointing over there. Magenta is somewhere there, and cyan is up, right? And now we sort of visualize the shape. Now, why does it help us to get a normal map? Well, because now those people who either took computer graphics at some point in their past or have some knowledge of what graphics does will tell you if I have normals, I can now use those to compute lighting, right? I can figure out position lights in my scene and figure out the interaction between those lights and my surface. And why is that good? Well, because, well, many people in this room can probably draw this. I don't know if everybody, it does require a certain amount of artistic talent, but it's relatively fast if you know how to draw, and you can sort of cheat a little bit, even if you don't, you can do something reasonable. Getting an image like this, that's beyond, I think, the capabilities of most people in this room, and it also, even if it is within your capabilities, it's extremely time-consuming. Now, why do we want to do it? Because both types of drawings are routinely used by artists. So, the first group, which is what I would refer to as line drawings, and notice that a whole bunch of them have those cross-section lines that I was talking about earlier, are the type of things artists use when they have just their initial cool ideas. Here is my cool idea, let me try and describe what it is. So they do usually quite a few of those. They are very fast to draw, and people know how to do that very, very well. But they also need the shaded imagery. Why do they need it? Well, because it's one thing to communicate with yourself, to sort of commit your ideas to paper. It's another to show it to a client and convince him that, hey, my design is really the thing you want. That's where you really want to have the object to be more real. You need to generate much more, concrete, much more detailed images. Generating with those takes a ton of time, right? You can sort of consider the distance it would take anybody to go from here to here. So what we are aiming is to start from here and to have our algorithm get us over here. But for that, what you need is, well, to understand what exactly do those cross-sections do, right? Because somehow we all agreed that yes, when I show you this picture, and pretty much if I would show it to anybody, they would recognize it as a back. But why? Why do we look at those lines and we understand the shape that's hiding underneath? And before we get there, just for those who do graphics and for everybody else, how does this relate to other work? Well, there had been a lot of work on sketch-based modeling. Some of you have seen from the videos, some of you might have heard talks. So people have been trying to say, okay, if humans can sketch shape, computers should be able to understand those sketches. And they had been saying that, I think, since the late 60s. And it had been something people had been trying to do, trying. And where people are is usually there are two types of approaches which work reasonably well. One is what's called multi-view, where you draw your lines one incrementally in a very particular order, rotating your canvas. I'll show a quick video of that later on in my talk. It's quite time-consuming. It requires understanding your objects. You cannot, and it requires rotation in 3D. It differs from the standard framework where you scribble your shape on a whiteboard and everybody understands what you draw. You cannot do this in any one of those softwares. They won't understand what you're talking about. There had been also a lot of use of all kinds of annotations. So you go to a drawing and then you say, well, actually this thing here is a cylinder, and this thing here is a sphere, and then if you sort of explain to your code, to your algorithm, what it's looking at, methods can do all kinds of pretty decent outputs, but you need a lot of explanation, you need a lot of UI. In contrast, what we are aiming for is, well, give my algorithm this, just an image, and ask it what to do. And as I said, what we are aiming for here also, we are aiming for a slightly easier problem. We are not aiming for modeling, we are not getting out a full 3D model. What we are getting is a normal map. Why? Because normal maps are what we need for the shading application that we are looking at. There had been some other work on getting normal maps, but those had been looking at silhouettes, and well, if you have only a silhouette, you get what you expect. You get the blob, right? You have a silhouette contour, you don't know enough about what happens on the inside to get anything better than a blob. With this understanding, with interpretation of those cross-sections, which is lines which artists are used to draw. If you look at artistic drawings, artistic sketches, these guys, those are cross-sections, are pretty much everywhere. So with those lines, if we understand what they mean, we can generate the shading. People would actually agree with this, yeah, that's what I intended on this model. Now, what's the challenge here? Well, we need to understand where and why artists draw cross-sections and how do people understand them. Because, well, yes, they draw them. But why do they draw them? When you talk to artists, the answer is, well, yes, cross-sections explain shape. That's a very useful statement. It doesn't tell us anything about, okay, how do I make my computer understand the shape the same way? Now, what I'm going to suggest here is our hypothesis about how that happens. So, why do artists draw them, where they draw them? Because artists are not drawing them in random places. Artists are indeed drawing in the places which are necessary to explain shape, except they don't necessarily know to quantify what that means. And it's very much related to how people perceive it, because the whole point of an artist drawing those lines is so the viewer will actually understand what the artist is drawing. So there is this strong backlink, right? Between an artist trying to make the object as clear as possible so that people will actually understand it. So there's two strong linkages here. And what I'll talk about is what do we think that artists do? And then I'll validate it through, well, both the algorithm I already sort of mentioned for normal estimation and through perceptual study. So should you check, you the audience and people in general do see those things the way we argue they do. You had a question?
So there are situations where you don't really have normal, if you have corners or something. So what kind of smoothness assumption are you?
I didn't make any assumptions.
Okay.
Yet. I just said, okay, I didn't say anything about smoothness, right? I mean, I spoke about cross sections. And what are they? Now, if you have a cube, I wish I had a marker which actually would show, I don't know how many of you can actually see the lines I'm drawing. Well, you can actually, after I discuss cross sections, you can actually argue some of those guys are cross sections as well, but that's orthogonal. Perfect. Yeah, markers, which actually work. Good. Okay, so, well, let me ask you a question. Let's look now at this picture again. And let's look at what do those lines tell us. And what I'm going to tell you is, if you look at every line, the line by itself, if you look at the cross-section line, it doesn't actually give you that much information. Where the information is hiding, and that's the most interesting observation. The first observation we made is here, and here, and here, and here, and at each one of those intersections. That's where our eyes go and say, oh, that's where the normal to the surface, I can take a good guess as to where it should be pointing. And now the question is, why? So what do we see at those intersections that makes us understand what happens? So what do you think? That's it. You look at those cross sections. What kind of relationships between them? I mean, you know the 3D geometry here. So what kind of relationship is holding here between the 3D cross sections? Suggestions?
90 degrees.
90 degrees between who? Yeah, between?
Between the two cutting planes that produce
Right.
the...
So the first observation, and if you look at where artists draw them and how they draw them, is, again, artists are usually circumspect about what they say, so there are no, when you look at artistic books and you try to look for advice as to where the heck do they put them, you would find a sentence that say, well, it's usually a good idea to make them perpendicular. Now, if you start looking at imagery, you find wherever they draw cross sections, they are perpendicular. And it agrees with research studies on how people perceive planes. It's related to this work from McRae had done actually study in terms of choices of planes. People were asked, okay, here is a 3D model. Now select a bunch of planes to cut it. Everybody picked orthogonal planes. So the first observation indeed we made is, well, when we look at those cross sections, they are not randomly positioned. They are always, in every image we looked at, drawn in orthogonal planes, right? So if I define a plane for my cross-section, remember I said cross-section is planar, those planes are going to be orthogonal. What else? Physicality. Now I'm sort of, guiding you toward answers. What else is interesting? What else makes those lines so effective? Yep.
So the curvature of the line
Right.
gives you the shape of the roundness.
Curvature. So that's a word that mathematicians don't often know, but well, there are enough people here who took some kind of maths at some point in their life. And yes, there is a strong correlation between curvature lines and the lines the artists draw. Now notice, a lot of curvature lines are not going to be planar in reality, but the cross-sections that artists choose are typically very close to curvature lines. So, the way the artists word it, cross-section on the surface explains curvature. So, it's not, so if a mathematician was to write it, he would say cross-sections are principal curvature directions. But the people who did the perception research are not, or the people who do drawing don't always know those terms. So there is an interesting, very much related observation for perception literature, which is this image on the bottom, which says, okay, let's say I have this lovely cylinder. If I draw these two lines, which are aligned with principal curvature directions, and now I just put them in isolation, people will interpret this area still as being symmetrical. If I take these two lines on the same surface, and I only draw those lines, right, without the boundary of my surface, well, everybody pretty much in this room would think this is some kind of a ball, right, if you look at this corner here. So yeah, there's a very strong correlation between those lines and curvature lines. Now what does that mean? Well, the most important from a numerical point of view observation is, well, principal curvature lines are always orthogonal to one another. Principal curvature directions are locally orthogonal, which means the two tangents will have to be orthogonal. Now, there are a couple more things which come up, and I will just list those, because the first two are not sufficient to get your geometry. The first two are very good observations. They always hold, but they're not enough. Another observation, which, again, you sort of look at, again, both at where artists mention where you should put them, and you look at perception studies, and what they indicate, they say, cross-sections are essential to achieving symmetry. Again, a very sort of, artsy way to say it, but what effectively it says is most cross-sections, not all, most, and that's where the difference comes, is most of them are drawn along lines which are local planes of symmetry. Right? So locally those cross-sections, not all of them, and we'll see examples where it's not the case, but locally there is strong preference for planes of symmetry, and for those familiar with mathematics, planes of symmetry are strongly related to local geodesics. So you have the same thing, asking your curve to be a local geodesic, or asking the plane to be a plane of symmetry. Now, it's not always the case, because local geodesic, you can express it this way. I'm not going to go into the why this formula will do it for us. I'm skipping that part. Now, just to point out that's not always true. So here, both of these planes are indeed planes of symmetry, right? They're cutting the object exactly in half at the reflection symmetry. But that's not always the case. So here, on a cone, this plane, the vertical one, is a plane of symmetry. The horizontal plane is not. And if you look at artistic imagery, so this is cross-sections on two-spaced, the vertical cross-section plane is indeed a plane of symmetry. This one, right, this ellipse here, is not. Right? If you cut the object around the ellipse, the top and the bottom are not the same. So in general, it's a weak cube. It's something which we look for or want to minimize toward, but it's not going to always hold, and we don't want it to always hold, because there will be cross-section where that's not the case, but it's something we do want to go toward. And then there is one more very strong hue, which comes actually from the entire image rather than from the individual cross-sections. Yeah.
Could you back up one slide? I was just...
Yeah.
This seems to be similar to a thing that comes up in computer graphics where in doing specifications there's the up arrow or ankle, whatever, and the way it's usually formulated, you're not required to be literally straight up because you just take the appropriate projection. And it seems to me, maybe I'm misunderstanding, but it seems to me, I think, isn't T1 the thing that maximizes the component that's perpendicular? Like there would be no other choice that would be better, even though you don't get the zero.
Actually, yes and no. In a sense that if you try to actually maximize it as your geometry, you might not get the right result.
Oh, yeah, but in this case, it does maximize it. And
in this particular one, yes.
yeah, I mean, I'm sure there's cases where that's not a good heuristic, but it's an over-constrained system, right?
Exactly. You don't want this to be equality. You don't want those to be enforced as equalities, for sure. Now, and I would say there was one more very important observation, and that has to do with the whole image here, and effectively with what I would call, and I'll just tell it what it is, because it's something you take for granted when you see an image drawn by an artist, but it's not something which should be taken for granted. And that's the choice of a viewpoint. When artists choose a viewpoint for an object, they don't do it randomly. Right? You can draw this bag from all kinds of views. This is the one which is most effective, because this is the one you actually recognize. And this is what's referred to as minimal foreshortening, expectation or assumption. And vision people sometimes refer to it as an accidental view. And basically the idea is, when you draw an object, you try to minimize the difference between the depth coordinate and what you actually see. So if you have a totally flat object, well, you draw it just from your front, because then you actually can see everything, and all your distances are the same, but most objects are not completely flat. So you need to have some distortion, right? I mean, the distance in 2D on none of those images will be exactly the same as the distance in 3D. It's impossible. But what people are trying to do, and they're looking, and it's something which artists are very much aware of, trying to find viewpoints, view choices, choices of poses, choices of positions, such that you actually can see objects. As a good example of it, we will never see a person, from the, this pose. If you ever want to have a drawing of a person in this pose, it will be in some kind of diagonal view, right? It will never be drawn from the front of the fingers. If you're looking at it from the front of the fingers, you have no idea what the heck you're looking at. So there is really a strong focus on trying to get a good view. And what it means for us is you want the change in Z between every 2 points, so let's say if we're looking at the tangents of our curves, to be minimal. You assume that the artist drew it from a view where minimal change happens in the depth. Because if there is change which you are not aware of, well, then you don't understand the shape. So this is the way we express it. So these are the key cues. I skipped one, which has to do with convexity of shapes. If anybody wants to look at it, the details are in the paper. But those are the key ones. Well, that's what we claim, at least. They are. Now let's see if we actually can prove to you that this is the right stuff. And well, the first thing I will look at here is this normal estimation, and promising. So what we are doing in the algorithm is we start from a sketch which is annotated, and you can pretty much recognize what this object is, I'm assuming, right? Everybody can see what it is? And it is annotated in the sense that we have the cross sections, and then we have the 2 other types, the silhouettes and the boundaries. It really doesn't matter that much whether the silhouettes and the boundaries are annotated correctly. We mostly focus on the cross sections. Now the first thing we do is we use those 4 observations I just listed to take a good guess at what the planes of those cross sections are. And for that, what we do is, well, we know the 2D tangents at every intersection, right? You can always, it's 2D, we have the xy. And now what we're going to solve for is the 3D tangents and the actual plane equations. So what is the normal of every plane and what is its offset? And for that we end up with a fairly scary and constrained nonlinear optimization, but luckily MATLAB and other solvers can do the job for us. So what we're going to minimize in this formulation is the geodesic alignment, or this expectation of symmetry, and the minimal foreshortening, subject to constraints which try to make the planes orthogonal and the tangents orthogonal. Those are inequality constraints. Why? Because yes, they're supposed to be orthogonal, but people who draw pictures or who draw images are never drawing their images perfectly. Yes, I drew these 2 here, and they sort of seem okay, but if you look carefully, probably my tangents are not exactly the perfect tangents on a sphere. Well, I cannot draw perfect spheres. So people's drawings are not perfect, which is why we need to handle things using inequalities to allow for the error that people get when they're trying to draw stuff. And we do enforce some hard constraints which just link the information to one another. For instance, we do assume that when we have 2 curves intersecting, that's a shared point. That's sort of a good idea, right? When we see an intersection in 2D, it should be an intersection in 3D. So what this amounts to is a bunch of medium scary or not so scary equations with a bunch of non-linear quadratic inequality constraints. So what makes our life hard is these guys here. Because quadratic constraints are not particularly nice, as most people who do solvers can will tell you. But, well, we can still solve those. And once we get the planes, well, the next thing we do is, given the planes, you can get the normal at the intersection, because then you have the 3D tangents, and then you can do a cross product of those 3D tangents, get normals. There is some work to be done in terms of how do I get from normals at those points to normals all along the curves, and finally to normals all across. And well, now we are ready to play. So now we can get pretty pictures. And just as a validation, so the two images over there, the input curves, were created not just by drawing, not by a person drawing on paper, by using 3D software. We actually had a 3D model underneath, and we drew those curves on top of it, so we know exactly what the curves are, and we know what exactly the normals on those surfaces are, and this is our reconstruction. So you can see the difference, or not see the difference. If you look closely, there are some differences, but it's pretty close. So this is the ground truth, this is a perfect result, this is actually the original real shape, this is what we get. Okay, so very nice, but now we need to actually sort of validate, I mean, I sort of convinced you that, yes, this is how people perceive this stuff, but it would be nice to actually check that. And for that, let me actually switch here, and look at this little critter here, and let me just make zoom out here. So this is a little study page, which actually everybody here is welcome to just play with yourself. And what you have here is, you have a bunch of cross sections, and we asked users, okay, here is a picture, now try and draw in which direction the normal at this point is going. So this is the one just for testing, so there is actually a suggestive normal which sort of says, yes, this should be going there. Hopefully everybody here agrees, maybe not. Anybody doesn't agree that this is the direction of that normal? So think about, where is the surface pointing? Okay, well, here is, now, actually let's do the experiment. So, here is a bunch of crosses on an object. I would like you to raise your hand when I'm pointing the normal in what you think is the right direction.
Yo.
Everybody did it at the same time, right? And that's what's interesting, is that, well, let's do one more just for the fun of it again. Let's see what happens. Hands going up, hands going down. Okay, who wants to commit and hold their hand? Here? Up?
Yeah.
Yeah.
You need Rob Cook's green-red paddles.
Yeah, I do. Okay, so you can do this test. I'll show them, there is a web page, I'll show it that where you can go from it to it, just to experiment with how, whether you and other people think the same. But there is, so what we wanted to answer in this study is two questions. A, does everybody think the same? Which is sort of a useful answer to know, because if different people think differently, well, then those cross-sections are sort of useless. Right? If people have different opinions about what the shape is, that's not a very good tool. And we also wanted to know whether people and ground truths agree. As in, if we have real 3D models where we took those curves from, do we actually get from people the right results? And lastly, does our algorithm agree with the audience? Because we would like it to agree with the audience. So here is sort of answers. So you have three types of lines here. Red is a collection of all the lines from a bunch of users who took that study at that point. Black is green is ground truth, namely those are the model, the treble, the ellipsoid is a real model. So we know exactly where the normal should be. The toothpaste is not. So on the ellipsoid we have ground truth, as in here is where those normals should be pointing on this shape. The toothpaste is a sketch, so we don't have ground truth. Black is what our algorithm is saying. So what you can do, and I encourage you to take that study, is after you finish the study, it actually shows you where your guesses were compared to others. Now, what is interesting about those results is once you look at the median differences between people, namely discount some outliers, which are going to happen because some people either change their mind or just get confused, the numbers are remarkably close. If you think about those are degrees, right? 10 degrees is something like this. Right? The answers are both remarkably close, as if people give the same answer, very similar answers. They're very close to ground truth, namely people are pretty good at estimating the normal direction from those cross-sections or crosshairs, and well, our algorithm is also pretty accurate. So that was a very good thing, because it means that yes, we seem to be sort of providing a good hypothesis, yeah?
How motivated were the human subjects, and were there any timing constraints? Or
No timing constraints. It was more of a favor thing, so it wasn't mechanical too. It was more, here is a bunch of people I know in the lab. So but there were art students, a bunch of art students, a bunch of CS students. I don't know the exact mix because my colleagues in Toronto did it, but it wasn't a mechanical Turk setup where they have no control kind of, there's no motivation. So here I would say they were motivated to try and give the good answers. Yeah. So we didn't have to do it, say, the all kinds of double checks to make sure people are just not fooling around. Which would be a problem if, let's say, you did a mechanical Turk study. So here it was people whom you could sort of trust that, yes, they would do the best they can. But at the same time, they were not authors of this in any way, so they had no clue what we expected from them. Right? It was sufficiently hands-on. And then basically, I think we sent, I know what it was. Part of it was just sending that link. There is a big community of people who are using some of the tools that my course has developed. I think part of it was just basically sending a link to that community and saying, hey guys, would you mind giving us some input? Yeah, I think it's a good question. So, pretty pictures. I promise pretty pictures, it's computer graphics. So, you can recognize this shape, presumably, and it's fairly simple. This is what the normal map of it comes out, and this is the type of cool stuff you can now do. And, well, it's pretty neat. You can also, this came out, this was originally an actual sketch. We just overtraced our lines on top, and you can overlay it with the sketch. You can get really cool effects. Here are two other sketches, and again, well, you can do pretty cool stuff with them once you know what the normals are. Something which is quite a bit more complicated. Here we use multiple layers in the images because there are multiple sort of parts, one on top of the other. So the sketch contains several layers of lines. Again, pretty cool stuff with very, very minimal input. And one of the cool things is once you have normals, well, you can change the color, you can change the direction of the light, you can change anything algorithmically, and you get new pictures basically without any computation. So, just summarizing this part and seeing if I have a little bit more time to talk about some other things. Well, I would say the interesting bit for me was the mathematics here. It's trying to answer questions about where do artists draw lines and what do they intend those to convey, and whether what they intend is what people actually understand, which should be sort of a reasonable assumption, right? That artists draw things in a way that they want people to understand them the same way they draw. And we said yes, because, well, if we have basically that was part of the validation in the study, which said yes, if you have cross-sections, people understand them pretty much the same way. If you take a whole bunch of people, they'll have pretty similar understanding of what the shape of that surface is. And what we got out of it, well, lots of pretty pictures. And here is how the interface looks, so the kind of stuff you can now do. As you draw your lines, the algorithm gives you some suggestions of where it thinks the normals are going. And once you do the computation, well, you can now get your normal map And, well, because you have normals, now you can just move the light around. And you immediately could get a new picture. And now I have a little bit more time, maybe, because we started a bit late. I'll just mention another problem. But before I go there, if you want to look more, and if you want to try and do the study yourself, crossshade.com. And an important bit I forgot to mention somewhere in between. This is work done, well, I mentioned already Karan Singh, who is in Toronto, and his student Cloud Chow, and Adrian Wasso from INRIA Sophia Antibodies. It was published last year. Yeah.
I imagine it's really hard for someone to actually, if they have a shape in their mind, to actually draw it with these crosshairs. How hard is it? Because none of the things you did basically gave us that challenge.
So I will put it like this. If you are a designer, you are used to doing crosshairs. It's basically, if any design book you open, every second page you'll see sketches which have cross sections. That's about as common as they are, if that gives you a sense. So if you took a design course,
they might be a lot more approximate than you're assuming they are.
well, all the imagery I showed here, all of this, are designer sketches which go traced. So in that sense, they're super common. How accurate can you be? That's why we are using inequalities. So we are not really enforcing things, we're assuming, yes, your artist is inaccurate. Which is actually one reason, what all I'm showing here is shading, and we are not trying in this work to do actual 3D reconstruction. 3D reconstruction is much harder, because that's where that inaccuracy will come and bite you. But for shading, if your normal is 10 degrees off, you won't see much of a difference in the lighting. So even if the artist drew something inaccurately, as long as you get the sense that yes, this is pointing up rather than front, it will still look good. So you have a pretty good tolerance for inaccurate drawing.
And how did you get those errors, the epsilons in your? So your inequality rates and epsilons for the tolerance. Yeah. How did you get those?
Trial and error. I mean, we use the very accurate epsilon for ground truth, where we know it has to be by God there. For other stuff, I think it was more or less making I think it was pretty much 5-degree difference. So rather than 90 angle, 85 was still considered acceptable. If I remember, it was the arc cos of 90, of 85 basically. So basically it assumed that up to 5-degree accuracy is still close enough, which is what we saw in the sketches we worked. And yes, those are artist sketches, yeah. If I were to draw, probably you would need to increase that epsilon a bit. Okay, so I'll just touch a little bit on another topic I wanted to discuss here. And that's, well, what I talked about here was 2D essentially. Namely, we took 2D curves and we got 2D shading. Now, if you want to do modeling, you need to do 3D, right? Because objects around it are 3D. And one of the problems we have been very much interested in is how to link, how to get from either 2D directly to 3D, which is very hard, because this is 2D, maybe you understand this object, maybe you don't. So if you don't, a computer won't. So what we said, we looked, now there are tools, I mentioned them already, I'll show a video in a bit, which provide people with the ability to reasonably easily, make it careful, create 3D curves. You can get something like this lovely wireframe. Again, these are designer curves. These are curves drawn by somebody who actually wants those curves to convey a very clear object. Those are not random curves in 3D. And, well, I'm assuming most of you have pretty much the same interpretation of those curves as the one shown in this surface. I'll just actually run the video twice here. And just stop it. Here are your curves. Notice we are no longer talking about cross sections, right? Some of those may be cross sections, some of them any other type of curve. There are plenty of curves that artists use. But somehow those curves are very effective in conveying the geometry. Right? And so the question we asked is, okay, you can create curves. And there are softwares out there which you can use to get curve networks. But if you want a 3D model, you want a surface. So how do we get from curves to a surface? And why do we want to do it? Well, because curves are relatively easy. So here is an interface which lets you rotate. That's the part I mentioned, right? You can rotate things in 3D, and you can, in the process, create your curve networks. It takes time. It's not as fast as this looks, but you can do it. It's not easy, but doable. Getting from those curves to 3D surfaces is hard. That's the part where most codes basically for now stop and say, okay, now you go and manually create your surfaces using whatever softwares are out there where you are trying to maybe split your loops and do all kinds of stuff. But what we said is, well, but somehow when people look at those networks, and those are designer networks, right? Those are nice networks which the designer made so that somehow they convey the shape. Why do people understand that shape? We want our algorithm to do the same. So this is work with Misha, who is sitting over there, Tsa U, who had since graduated, and Karan Singh again, and was presented at SIG-Asia last year. And so what we want is we want to somehow go from this wireframe to this surface, right? And I'm supposed to skip those. There is some work which is related to that, which tries to fill in holes. So you have a curve in 3D. Imagine this is 3D, and you want to put a surface into it. And, well, if you have 4 sides to this hole, people who are taking my modeling class, and there are a couple of them here, will tell you, there is a lovely tool called Kunstpatch, which was developed in the late 60s, and people have been using it ever since. And it's fantastic, and all the artists go, yay, this is what I expect to get out. But, well, what happens if you're boundary? And again, imagine all those 3D curves. 5 sides. Or your boundary does something. This was a bit extreme because this is the point where we start going away from designer curves, as in curves for which when people look at them, they understand intuitively what should connect to what. And the answer is, well, there has been some work which says, okay, you have something weird, put a point in the middle, do something like that. Sometimes it works, sometimes it doesn't. If you have something which has concave boundaries, it doesn't work. So, and those methods are really looking sort of from a geometric point of view, rather than, okay, how do you get something which agrees with what people actually expect? What we want is to look at what do people expect when they get those inputs. And again, if you ask people, and okay, stop this, okay, go on. If you ask people, let's say in physics or in mathematics, well, I have a curve loop, I have a closed curve. What should be the surface in the middle of it? Ask any physicist you know. They'll tell you, it should be an Laplacian. Of course, everybody knows it. It should be a membrane. That's what a membrane looks like. That's not what you expect when you look at that curve, right? So why is that? Well, that's also linked to the part where why do people like Kunstpatches? As I said, I mentioned the term Kunstpatch because when you look at that loop, what you sort of imagine, and I will sort of tell you what you're imagining, hopefully you agree with me, is that you have a bunch of lines essentially kind of going from this side and to this one, and in the opposite direction. Now, this is what people, if you look at art books, that's again, where they have this term, which is flow lines. There's a flow of a surface. No mathematical definition. But talk about this flow. And they talk about the fact that the lines that they draw are the major flow lines. that they capture all the important flow lines of your object. And when we talk about flow, it's this fuzzy term, but again, it's roughly related to curvature directions. If you look at where artists put those flow lines, they tend to put them along principal curvature directions, but loosely, because for instance, if you have a sphere, you don't have principal curvature directions, but you still put your lovely network, which I'm assuming everybody is well familiar with, right? Everybody saw this representation of a sphere, right? Those are not really those are not necessarily a curvature network in the sense that there are no principal curvatures on a principal curvature direction on a sphere, but this is the type of stuff they refer to when they speak about flow lines. So in our heads, we all have this sort of notion of what those lines are. We see them, we are used to drawing them, we are used to seeing them. And the question becomes, okay, if artists draw principal curvature lines, this or not, this is exactly this ambiguous case we mentioned earlier. If you have garbage in, garbage out, in a sense, if you have a random curve in 3D, well, nobody knows what's supposed to be there. If you have an artist-designed 3D network, then artists put those curves in places which matter. They put them where they really convey shape. And what designers draw? That's the terminology that's often used. Sparse representative flow lines. Yeah.
So if we don't know which ones are at the back and which ones are at the front, there are two representations for each of these.
Remember, I said the curves are always I'm showing now 2D pictures. In reality, my input is 3D. Yeah. And that's a point just good to reinforce. So the first part of the talk was very easy because I was showing 2D inputs, and 2D inputs on paper, or 2D screen, are very easy to understand. These are 3D inputs. Yeah. And 3D curve networks, people have trouble understanding the shape. So whenever I'm showing something like this, usually I'm trying to have grayed out the lines in the back, but you have to use your imagination. Yeah. Or when things are rotating, which means you can see the 3D. Okay, so what I'm going to try and do here, and I'll just rush through it, is, as we said, I argue what views I really envision is this network that I'm showing here. So those are flow lines which are connecting points of boundary. And when you look at what artists do, so this is an example where we can start with that wireframe of a boat and of another model and gave it to an artist, paid him money, and said, okay, now create a surface which surfaces this model and surface it with squads. Why? Because that's sort of a standard tool. And when you look at what they do, you really see this pairing of what's perceived as opposite sides, right? You see those sides, those are the ones which are highlighted here in the coloring, and you see these sort of lines of surface going from one side to the next. So what we are going to try and do, or what we did, is to try and solve this problem of pairing. And again, here is a network. This is rotating as 3D, so you can try and envision it, and hopefully you will agree with me when I'll show you the matches. Right? Those are the sides you would sort of connect as the pieces on your surface. Now notice that what happens when you're doing these connections is you're connecting sub-elements, right? So in this case here, essentially the visual connection connects these two portions and these ones. So effectively we introduce this point which is not really in the geometry. It's not a corner, it's not a sharp feature. It comes out of this need to pair these two sides and these two sides. If I go back to the image, let you see the wireframe, because I know what it is, so I might have just run it a bit too fast. So you could try and imagine it here. You could sort of see what this is in 3D and try to imagine the surface. And you'll see that the surface is really, you sort of think about it as these two sort of cylinders, right? Pieced together. Now, what our challenge is how do we find this pairing? Now, if we had those corners, then people in theory will like what I'm now going to say. The right different argument we argue is the right algorithm for pairing, if we have the segmentation, is what's, I'm blanking. I blanked on the name. Stable marriage. Stable marriage or stable matching, which I don't know how many of you have ever heard that term. It's an algorithm which had got a lot of exposure recently. There was quite a bit of a terrorism about it. One of the well-known algorithms now is a game theory. And this is what we argue is consistent with what people see. The reason we argue for stable marriage rather than some L2 optimization is because what we think people do is they first pick the most obvious pairs and say, okay, these two are for sure paired. By God, they have the same shape and they're exactly opposite. They should be paired. And then everybody else sort of follows. And that's what stable marriage or stable matching algorithm by definition does. So what does stable marriage? It means if you have a bunch of women, a bunch of men, and you now say, okay, I want them to be married such that no couple will have any incentive to divorce and marry somebody else. What it means is no two people who, let's say, there are no two people who like each other more than they like their spouses. I mean, they might hate their spouses, but at least one of them hates the other even more than the spouse. That's why stable marriage. Now, the challenge, though, so there are two challenges here. First is that we stipulated that this is stable marriage, or stable matching, because here we have no preference.
The key theorem is that there's always one exists.
Hmm?
The key theorem is that there's always one that exists.
Yes, exactly. That's another one. But one of the challenges we also have, we don't have the segmentation a priori. We don't know that this side here has to split. So I'm not going to talk about the algorithm. I'll just show maybe a couple more pairs. Here is another matching, and here is the surface. I'm going to skip a whole bunch of stuff and just show some pictures. And once we have those pairs, again, there's a bunch of processing going on, which is, I would say, not that exciting, but if you want, you can look at the paper, which constructs from the pairing the actual surface. But the hardest part is finding the pairing, in particular because, yes, you need to split sides in not obvious places. Because you can start by splitting, let's say, the sharp corners where it's sort of obvious that things might change. But the hard part, and there are enough theory people here who want to look at that challenge, is how do we figure out when and where to do splits so as to do the best matches? Like, we are not claiming that what we did is the best thing ever. If somebody wants to look at how to do that, you can see some teary faces in the audience. So here are some more results. So here you have networks with sort of 5 more or less equal sides, 6 equal sides. You get fairly predictable results, what you would expect to get. Here are some more tricky bits. Again, trying to take the pictures in 2D as if so you can still imagine this 3D pretty well. And you can see again, it agrees quite well with what you would have done had you been doing this manually. Sort of, again, the type of sort of unions of cylinders we have seen before. Here are some more interesting inputs. And one of the challenges on networks is you want your surfaces to fit or your quads to match well across boundaries. Again, I'm skipping the details. Another one, starting from again, an artist drawn network. Again, key artist drawn, not random. We are not trying to put a random surface on a random network, because random in, random out. What we are looking for is if an artist drew this, they knew what they were doing. So let's try and guess what they were doing. And what did they expect? So here you can see some non-trivial shapes. Again, being able to match what is going on there, right? There's quite a complicated boundary, and matching automatically the parts which should correspond. Again, some more interesting models. Weird kind of stuff where you sort of want the matching to fit. So, to conclude, this was the first method to quadrangulate or to even surface designer networks in a way that tries to aim to capture the intent of the designer. And the key idea was basically was this understanding what designers want to a certain degree, this notion of flow lines and what does it mean, sort of your significant flow lines, and this concept of matching, in a sense, understanding why do designers like coarse patches so much, because they do. Nobody really sort of had an opinion, understanding of why in particular. Now we can argue that we know why. And in order to solve the problem of how to find those matches, that's where we use a stable matching algorithm, or a stable matching. Now, as the limitation, we are not looking at the network as a whole. In a way, it probably should, because the network gives you extra cues in addition to just an individual curve. So, take home message from the whole thing. Well, artists know geometry. They just don't know it's called geometry. Namely, they do, when artists do make certain choices, designers in particular, because they are taught design, so they are taught certain choices, which are very good choices. They don't know necessarily why those are good choices. They just say, okay, this is a good idea to do this. But they don't necessarily know how to quantify it. And that is inexplicably linked also how observers, how we see geometry today. Because we, in our consciousness or subconsciousness, know what the curvatures are, I'm not sure, or because again we have been primed by looking at artistic drawings, but we know how to interpret sketches. We know how to interpret 3D curves. The big interesting challenge is, okay, how do we try to quantify it? How do we try to come up with the mathematics underneath it? How do we try to validate it? And how do we try to take advantage of it for algorithms, for computation, for modeling? Thanks. Time for questions? Yeah, Holger?
So Alla, these things that you said about, the things that artists know but don't know that they know, I assume that quite a few of them they have to develop as part of their skills. So I'm kind of wondering about the inverse problem, right? I mean, is there something in what you are doing here that could be inverted to help them acquire these skills better? For instance, if you have a 3D model, right? I mean, one of the challenges I think that designers go through is, or basically when they learn sketching is, here's the thing, sketch it.
Right.
And so it seems that there would be a way where you would say, well, here's actually a set of really good curves for doing that.
Right. So the answer is yes. I think there definitely is a back loop. In a way, I mean, it's interesting. I mean, there is work of also looking again, where are the given 3D shapes? Which lines do artists choose to use to draw them? It's interesting. I mean, there's some things that everybody agrees on, like, don't make it say, what's called ridges and valleys, which is lines of extreme curvature, and sharp feature lines. But the question of at what point do you want to draw cross sections? That's why it gets quite interesting. I don't know the answer necessarily, but I think it is a really good question. Okay, what would be an advice of, okay, at this point you drew enough of them so that nothing interesting is happening. Because the key thing about this type of sketches is you make the assumption that anything which is not drawn is not happening, right? If this sphere here in reality had a bump, somebody would have told you that via a line, right? You make this assumption that whatever is not drawn is boring. But that's actually the underlying assumption to a certain degree in this algorithm as well. It's like everything sort of, from a geometric point of view, the lines that the artist drew captured everything. Nothing interesting happens in between. Now that's why I think it's a good question is to figure out what does it mean, nothing interesting happens.
Can your algorithm come up with some measure of the ambiguity of a drawing so that if you're searching for these stable matches, then you could come up with an idea of just how stable the matches are and therefore reflect back to the user that, oh, well, look, this is potentially ambiguous and throw back multiple solutions.
I would be careful a bit because it's hard to say sometimes because it's a weakness of the algorithm. But you can give back the cost of the matches. We say if the matches are perfect, you have, let's say, 0, let's say in this case, it would be like this pair are matched completely perfectly, this pair matched completely perfectly. So you can get that back. I mean, I cannot say that that number is necessarily on the right scale for the artist. I mean, if it's not 0 or non-zero, I think it's meaningful. Whether it's 0, 5, or 1, I'm not sure.
The example with the basket, it seemed like, you know, again, sort of if you're thinking about how people think about it, I would have thought that, you know, you basically think about it as a bowl with a handle attached. And so the matching, you know, your matching algorithm basically had to segment in a way that created 3 lines that ended up matching, whereas really it's 2 lines that match the top and the bottom, and then you have this extra handle built on top. I just wondered if you guys thought about that, because it's kind of...
That's the other option you could sort of think of. Let's say you have, well, this is your basket. You could have thought about, okay, you first sort of cut it off, and then you treat it as 2 parts, but somehow, since there is no line between them, it means the surface has to be completely continuous. It's very, and then it actually, from a technical point of view, it becomes the same problem, because you need to match this interval that you created, this picture here, has to be matched somewhere to have the surface sort of go continuously. So you would still need to do this, but you could maybe do this first, and then your problem might be easier.
Just another question. It seems like the first thing you talked about, you had this nice thing where you also had this perceptual study that kind of confirmed your, you know, mathematical heuristics for perception. What kinds of perceptual, it's harder obviously with the curved.
Right. So what we did, I didn't talk about it here, is we actually, I mentioned the fact that we had an artist basically surface this thing, and then we compared qualitatively our results to the artists. And they're not completely identical, but they're very missing. So that was sort of our way of actually saying, okay, does our artist make sense? Was that sort of a good way of asking, okay, if we have an artist, would they get back the same output as you? And they did up to some of the differences, which you can then say, okay, the algorithm failed, or maybe there are multiple interpretations.
I'm just wondering if there's some other assumption about the actual existence of ground truth. In other words, I'm thinking perhaps of the work of Escher and impossible figures, and just wondering what in the world would happen if you set this loose on an Escher drawing.
Well, I won't use the word I was going to use, but basically, if your input is not well defined, well, you get a not well defined output. As if we are basically this as a second, well, this part, we're talking about the second half, right? It's operating under the assumption that yes, there are really a human, everybody in this room would come up to more or less the same conclusion of this input. And that's the conclusion we are trying to find. If every person in the room will have a different solution, God knows what our solution will be, because there is no right solution.
No, but the pleasant thing about Escher drawings is that there's this kind of local consistency, and in some sense everybody does come to the same conclusion. It's just that it's a contradiction.
Well, one of the actually interesting things about the Escher stuff, actually the moment, it's actually very much related to the foreshortening assumption I was mentioning, is one of the tricks in Escher's drawings is things which are drawn as straight lines in his drawings. If you actually drop the straight line assumption and assume that the 3D can actually curve, they actually have a 3D realization. Which actually is very much linked to this assumption, which is sort of a lot, really implicit in the way people understand pictures. When you look at something in 2D, you make very strong assumptions about how the 3D should look, and that's one of those, the straight lines. And there actually can be a solution for some of those in the 3D solve, in sort of like, let's say, this type of solve, except it will not be straight, for instance, anymore. Which is sort of an interesting way. Slightly off your question, but yeah.
So my question's somewhat related to that. In your talk, you use both the word artist and then design or designer at various times. And from having discussions with people at art and design schools, that's kind of like saying computer science and engineer and expecting it.
Designers.
Yeah.
Whenever I talk about designers.
Yeah, which
Corrected. I
yeah.
said corrected.
Well, yeah, so my point though was, let's talk about artists. So I think this relates to the ground truth problem. And there was a paper, and I don't remember the reference in it now, but it was like Graphics Interface in 1982, but it referred to some work that had been done in the 50s by a psychologist, and I'm misquoting here kind of on purpose, but they showed people pictures of hands, human hands, and asked them which ones look the best. And there were various kinds of renderings like you've had, but with cross-hatching and this and that. And stretching the truth only a little bit, what they found was the Disney picture of Mickey Mouse's hand wins. It looks more like a hand than anything else, but of course it doesn't even have the right number of fingers. And so now you have to ask the difference between art and design. If you're trying to explain to somebody how to use some machinery and putting your hand to turn a dial, it really doesn't matter how many fingers are on your hand. And if a Mickey Mouse hand makes it easier to understand the instructions, in some sense that's a design or engineering solution. It doesn't rely on the aesthetics. And of course an artist would say, I can have as many fingers as I want. So I'm not sure these are particularly easy questions to answer.
I'm not saying they are. I'm saying that maybe some of them we could try and answer at least in a way, that will help us. Again, making the assumptions the artist is not misleading you intentionally. Yeah.
So I think
in these cases, well, yeah, you can generate with, you can fake cross sections, right? Just rotate them 45 degrees, and now our algorithm will go, okay, what happens here?
And so I think that it probably comes down to a slightly deeper question then of what is the communicative purpose of the image? Because sometimes you're trying to sell things, in which case it doesn't have to be realistic at all, it just has to get people to buy. In other cases, it's for a manual or it's whatever, or if it's actually part of the design process and it's related to construction, then it may have very highly technical constraints, but it really is, these are always in the service of some purpose.
Well, the applications we are looking for are the design cycle. So, yeah, basically you are aiming to save people who are making designs time which goes into all kinds of steps that you can.
Well, do you have any thoughts on when you cross from bottom-up cues towards to top-down cues, right? And so, because if I've just been designing chairs, then the sketch you had of the chair right at the beginning of the talk, I would say, oh, sure, that's another chair, and you can start dropping more lines. And so, I think when we look at drawings, so presumably artists do this as well, they have to make a decision to what extent the drawing is truly bottom-up complete versus relying on the viewer's knowledge of a certain class of object, etc.
I would say that's the part that we try to avoid. That's why we are looking at the low-level cues as much as possible, because the low-level ones are the ones you can sort of distill into relatively simple, let's say, equations, relationship, numerical things. Say, recognize if it's a bug or recognize if it's a spaceship. That's where you get into like hairy stuff, right? Because I mean, that's where you need to start a special case of how does a bug look, how does a spaceship look, and well, as about to a 3-year-old, I can say that takes a lot of time to figure out what are all the bugs in the world. So, teaching the computer that will take a while. Yep.
To what extent does the symmetry saved? Like, does the bug have a fourth leg or not? Does the bug have a fourth leg in this?
I don't know. We don't know yet.
If we rotate it.
We don't know. This is, again, remind us, this is a shaded image. There is no 3D here. I'm cheating. I'm completely cheating, right? I have a normal map, which means all I know is where the surface is pointing. In this paper that I'm discussing, you don't know which part, how far, for instance, is this part, this leg, how far from in front of the body it is. It can be like that far or this far. Like, there is no depth here. So, no, I also don't know there is a fourth leg. There is nothing which analyzes that, right? There is no 3D. All I know is, given those lines, I can take a pretty good guess what the normals are. Yeah.
In this actual work, did you try to make any sort of attempt to use a 3D reconstruction in order to enforce some consistency for the normals, or is it just so noisy that it's hopeless?
You don't necessarily, well, you can do what's called Poisson reconstruction, which is you start from normals and try to get 3D. It's not really defined when you have depth discontinuities, and there are all kinds of issues. Talk to Brian, he's doing actually 3D reconstruction from this type of imagery, where you need to do use a lot more machinery than just the normals. So it's, yeah, getting a real 3D, way harder than getting normals.
Okay, let's wrap it up there, and thank y'all again.